All right, so I'd like to introduce our first keynote speaker. It was Stephen Boyd, who's going to talk about disciplined convex optimization with CVXPY. Pi.
Yeah.
And Stephen is from Stanford.
Good. Thanks. Wait. Anyway, there's several people, Claire, who were from Stanford in the audience. So I think it's not, okay. It's not a bad play. Okay. I just was checking because there was a hint. There you go. Okay. Actually, if you could just turn off the amplification in here. I don't need it. I teach the classes way bigger than this with no amplification. So, okay. I'll let them figure it out. That's fine. Oh, it happened. Wow. Okay. So I'm very happy to be here. So happy birthday, Shankar. So I'll just say, even though I have even too much material, so I shouldn't be taking up any time, I will say that I first heard about Shankar, but he was more like a concept. So it was Berkeley, 1982, and 81, 82, when I was around, and I just kept hearing about this mythical person who was like young and brilliant and energetic. And then actually I met him like about 1982 or something. And by the way, all those things turned out to be true. But they're still true. Well, okay, maybe. All right, but 2 out of 3 is not bad. Okay, so that's fine. So I remember that. Yeah. Okay. Okay. Oh, and I should say that I'm extremely proud to be one of your 25,000 students. So, I mean, it's good. So, okay. So I'll talk about disciplined convex optimization with CVXPY. This is, it's severely compressed, so I asked, Stephen Diamond, about this. I asked him, like, do the slides look like they make any sense? And he said no. So we'll see. So the idea will be maybe just some essential ideas will come out here. Okay. So I'll tell you a little bit about convex optimization first. Then we'll get to discipline, and it's really just about this, disciplined convex programming. And then CVXPY is then an instantiation of this. It's an implementation, and it happens to be in Python. But I mean, all that matters is that it's a modern language, right? Or okay. And then, if I have time, we'll get to it, and we'll talk about doing some distributed optimization. And it'll just be a way to show, what can you do if you actually implement these things in a modern language and how easy it is. Okay. So. I think a lot of people here know it, so I'm going to be super duper fast. That's an optimization problem. You have a variable you have to choose. You have an objective, some constraints. And the critical part is that the objective function and the constraint functions have to be convex. So they have to have non-negative curvature, right? If they have 0 curvature, it means they're linear or affine. And then that's a linear program. Okay? So that's a convex optimization problem. Why would you care? Well, it's really just 2 reasons. I mean, so actually, it does get clearer when you compress it sometimes. There's actually 2 reasons. Number 1, you can solve them, and number 2, there's many applications. That's it. So that's why you should care. Okay. All right. What we're going to do now is I'll tell you about disciplined convex programming, and this is actually kind of the bulk of what I'm going to talk about. And this is going to get technical. So just prepare yourself. Or even mathematical, right? Okay. So the issue here is you have to be able to identify convex, concave, and affine functions, right? So affine is linear plus a constant. And, that just says that they satisfy these inequalities. So affine is easy to detect because it just basically says it's a function that's linear plus a constant, right? So it's that's fine. So the question is, how do you identify convex and concave functions, right? And how would you do this? Well, I mean, you could try via the basic definition. This won't work for anything but the simplest things. It's a complete disaster, right? You could try it via second-order conditions. You find this in like an advanced calculus book. This also is totally useless, except in the simplest cases, right? Totally useless. And it turns out really kind of the right way to do it, and of course, not mathematically, but if you're actually going to use these things, the right way to do it is constructively. And so you should construct a function, and you should start with a library of basic functions that are known to be either convex or concave. And we'll see there's a few other attributes of them you'll have to know. So you have a library, and it's actually shockingly small, how small that library can be and still cover huge numbers of fields. Okay. And then you have some calculus rules or transformations. And also, it turns out that rule set can be very small, and in fact, one of the points of the talk is that rule set actually has cardinality 1. There's actually only one rule, so we'll get to that. Okay, so first, some convex functions. And I mean, there's some, functions of one variable, you just plot it in your eye and see if it curves up. I mean, it's not a big deal, right? So there's some obvious ones like various powers, exponentials, negative entropy. That's something related to the Kullback-Leibler divergence or relative entropy. Quadratic forms with a positive semi-definite matrix, any norm, max. And just to throw in something fun, the sum of the 5 largest entries of a vector, right? That's a convex function. In fact, so is the sum of the largest 3.5 entries of a vector. And you might ask what that is, right? But it's what you think it is. It's the sum of the top 3 plus a half times the 4th largest entry. Okay? So these are weird functions. I don't believe this has ever come up in any legitimate application. So it's only there just to be cool and to show off. So just so you know. And it's implemented in all these systems just so you can show off. I don't know. So it's possible that there's some legitimate application. Okay. So some basic concave functions. I mean, these would be things like, square root, geometric mean, log, quadratic form with negative semi-definite, min. Ones that are maybe not less obvious is things like log of the determinant of a positive definite matrix, right? So by the way, this has been known to be convex for more than 100 years. So, or the geometric mean of the eigenvalues of a matrix, okay? So these would be examples of concave functions. And you could go on and on with a few, but you don't even need this many. I mean, you need just a handful, as you'll see. Okay. So then there's some calculus rules, and you have to put these things together. So how do you put them together? And when you teach, human beings, this is how, if you teach a course on this, this is how you'd explain it. You would start with obvious things, like, hey, you know what? If you have a convex function, then 2.1 times it is convex. Okay? I mean, duh, right? I mean, and you'd say, oh, if you add 2 convex functions together, the result is convex, right? You can have affine, precomposition. Pointwise maximum. That's actually interesting, right? So you have 2 functions that go like this. You take the pointwise maximum. And actually, that's interesting because generically, that introduces a non-differentiability, right? So, okay. And composition, right? Convex increasing function of a convex function is convex. And there's like 3 or 4 more advanced ones and stuff like that. But it turns out you don't need to know them. Actually, it turns out that when you think about all this very carefully, it turns out there's only one rule. They all go to one rule, and it's just this. So here it is. If you have a function of k functions, then if the outer function is convex, this function here is convex if for each argument, either the argument is affine, or this function is increasing in that argument and that's convex, or it's decreasing and that's concave. Okay? So I did warn you that there was actually going to be mathematical content. Sorry. So it's happened now. So, that's it. So here's the cool part. It turns out this subsumes all of the other one, every single one. And so it turns out this is the only thing you need to know. Now, it's a bit weird, right? Like, for example, you could use this to show a simpler thing. Like, let's show that if a function f is, if f of x and if f and g are convex, then f of x plus g of x is convex. Okay? So the way you do that is you say, oh, I'll introduce my function h. And it's got 2 arguments, and it returns the sum, right? And then you say, well, let's see. It's convex. Oh, it's increasing in each argument. It's a match. Okay? So done. So, I mean, that's kind of a weird, pedantic way to show it. But it is interesting to know that there's actually only one rule. Also, if you're looking at this, you should be getting a kind of, I don't know, if you do object-oriented programming, that part of your brain should be like tingling right now. Because this is very close to that. And I'm describing it that way. OK. So the idea now is you do constructive convexity verification. So you start with a function given as an expression. You build a parse tree for it. And the leaves are going to be variables or constants and parameters. And then each node is a sub-expression. And then each sub-expression is a function, which is the local function of the children. And basically, they have to match that one single rule. Right? So that one single composition rule. Then what you could do is you walk through the expression tree and you tag every sub-expression as either convex, concave, affine, or constant. Actually, it's even simpler than this, right? Because affine is when you're both convex and concave. So the code is even simpler than what I'm saying right now, right? But this is not a bad way to think of it. OK. And a variation is you can tag the signs. Actually, that's interesting because, in fact, all you're doing here, this is absolutely nothing more than doing sign arithmetic on the second derivative. That's all you're doing, right? So it turns out, and if you think carefully about it, the entire thing can be explained as sign arithmetic on the 0th, 1st, and 2nd derivatives. Now, of course, these things are not differentiable, so that's just kind of made up. But if they were all smooth, that's what you'd be doing, right? And you're using, very deep rules like the sum of a non-negative thing and a non-negative thing is non-negative, right? So, OK. All right. So this is sufficient, but not necessary for convexity. OK. And this leads us to a discipline convex programming, which is the title. And so here's what it is. It's just a framework for describing convex optimization problems, and it's based on this constructive convex analysis. It's sufficient but not necessary for convexity, and it's the basis of a bunch of domain-specific languages for convex optimization, right? And by the way, it is actually a language. I'm going to show you essentially what's the Backus-Naur form in a few minutes. And by the way, by CS standards, it's a teeny itty bitty. It's an exercise, right? But nevertheless, it's a language, a domain-specific language. So, OK. So here's a DCP, and this is very close to just describing the syntax. Actually, it's not very close. This is describing the syntax. OK. So a discipline convex programming, it's got it may have an objective, and it can either be minimize a convex thing, maximize a concave thing, and it can have some constraints, and there's only 3 types. And this is, of course, just syntactic sugar. It allows you to write an inequality any way you like, right? But that's pretty much it, right? And then each of those expressions now has to be constructed, by a parse tree where every node matches that single general rule, right? So an expression, you form it from variables, constants, and this functions from this library, right? So you'll have a library. And the library functions have known convexity, monotonicity, and sign properties. And notice that these are essentially, even though, of course, the whole point of this is to do it for non-differentiable things, these are essentially the signs of the 0th, 1st, and 2nd derivatives, right? That's what this is, right? And then the key is this. Every sub-expression has to match that general rule. So if it doesn't match that general composition rule, then it's not in the language, right? So, and it's not a valid DCP. OK. So the idea is if you do this, then it's convex by construction, right? And this is very different from what you might imagine. You might imagine you'd say that the way it should work is, you want to solve a problem, and so you write down what you want to solve. And you say, here are my variables, here's my constraints, here's my objective. And then you wait while the verdict comes in as to whether or not your problem is convex. And you can make systems like that, and they're interesting, but they're kind of useless. And actually, if you think carefully about it, it's not the way you want to do it, right? So the idea is you want to be it should be thoughtfully convex, meaning, it means you should, to establish that one of these is convex, actually the rules are local and they're syntactic, right? So it's actually kind of cool. It means, for example, if I write out a problem and it is a DCP, a valid discipline convex program, then, for example, if there's a square root, I could swap it with 4th root because they have the same attributes, right? They're increasing, they're concave, and they're positive or non-negative. Right? So that's the idea. I could swap exp in the plus part, right? So this is the idea. OK. So now I'll tell you about an implementation of this. Actually, there's multiple. This is a recent implementation. There's maybe one of the first was maybe YALMIP, and CVX was another one. And I'll tell you about CVXPY. So this was something put together by Stephen Diamond, with me being a troublemaker. This is when he was an undergraduate at Stanford. So. And it's open source down to the solvers. And the idea is it's part of, it's Python, so it's real. It can actually be, actual real people can use it. So this is what that is. Ooh, OK. OK, I'll go on, but I'll show you an example, right? So it's pretty clean. And I'll just say a little bit about what these bits and pieces are. This declares, this is a constructor for a variable that says x is an optimization variable. So by the way, different from CVX, if you used CVX, which is in MATLAB, CVX, it's charming, CVX, but it's you know, it's a little like a little baby scripting things. And this is actually more real. And the interesting thing here is if you use CVXPY, variables and expressions and objectives and things like that, they live outside problems. They're independent objects and classes, right? So here, this is actually getting a little bit irritating. I could turn that off, or yeah. Okay, I'll just see what happens. Okay, so this forms an expression, right? And you could check if I could actually take this thing and okay, now that's getting really irritating. Okay, all right, let's see. What was that? Turn off my wireless. Okay, yeah, I'll. Oh, has it now locked this thing? No. Okay. All right. You know what? Let's not worry about it. I'll get physical with it if it comes back again. So, okay. So this forms you form a problem. So that's a problem object, right? And again, if you okay, fine, no problem. Oh, wait, there we go. Ah. All right. Yeah. Okay, so this constructs a problem. That's a constructor for a problem object, and it makes that's an objective. By the way, that's an expression. Minimizes a function that maps that takes as argument an expression and returns an objective object. So that's an objective object. That's a list of constraints. It only has one constraint, right? So the point is, it's quite readable. This is the idea. And then if you call the solve method on this problem object, it solves it. And one of the side effects of that call, of calling that method on that object, is that the value attributes are written if the optimization is successful. Okay, so this is the picture. If you haven't seen it before, it's kind of cool. Okay, so one of the nice things is, you know, once you're embedded in a real language, you know, as opposed to another language, and because this is being taped, I'm not going to say what that is, but you could guess. Actually, yeah. It's a good thing you said that, Claire, about how we were being taped. So, okay. So, I mean, you could do stuff like this. Here's it takes like nothing to actually, for example, do actual parallel computing, right? So it's nothing. You just get the multiprocessing package. You import pool. You get yourself a pool of processes like this. And you make a little function that does absolutely nothing more than this. It sets the value of the parameter, solves it, and returns the optimal x, right? So it's just a little wrapper, just nothing to it. And then here, if you did map, this would be you'd be calling the core Python map, which basically says apply this function to that list, right? And that would do it serially, right? In this case, it does it in parallel, right? So this is so the idea is, again, this is addressed to those of you who still use MATLAB. Sorry. Oh, I said it. Okay, sorry. Anyway, fine. Okay. Okay. So now we'll zoom along, and we'll look at consensus optimization to look at some distributed optimization and how this works, right? So, okay. So probably, you know, one of the simplest problems there is to solve with, you know, a distributed optimization is this so-called consensus problem. And it's weird. It looks very specialized, but simple. Actually, if you can't do this, you can't do fancier things. And if you can do this, you can do anything. So it's a nice. You should start always with this. In fact, in some cases, you can just finish with this because it's basically the same as everything. So you want to minimize a function, which is a sum of terms, right? And these functions can be plus infinity, so they could include constraints and things like that in them if you wanted. And a good example of this is in, like, you know, machine learning or statistics, where x is a vector of parameters in a model, in a data model. And then fi would be like the loss function plus, you know, regularizer, right? And so, for example, if you just minimized I is the ith block of data, if you just minimize that alone, that would give you the model that fits the ith block of data. This, if you minimize this sum, you're actually doing, you know, collaborative modeling or something. It's basically, it's the model you'd get if you collected all the data in one place and then fit a model. Okay, so, and the key is to do this in such a way that you don't move the data. So the only thing each one agent will mess with just fi. Will handle each I. Okay, so this is the idea. And you reformulate this in a way that looks idiotically stupid. You Instead of having a single variable x, you let everyone have their own opinion, and then you adjoin a constraint that says, but everyone's opinion has to agree. So, which does not look like progress. I mean, it doesn't look like. But then this you can now apply, many methods, like operator splitting methods or other methods, and you will get things that will solve that, and they will be distributed optimization methods, right? So if you apply something called ADMM to this, which is the same in this simple case as a bunch of others, like Douglas Rackford or some others, you get this. And it's actually a beautiful little it's very simple. It says that each of the xi's, remember, xi is sort of the opinion of what the global x is held by the ith agent, and in fact, in iteration k+1. And so this says each individual opinion should minimize, well, the local cost, and then simply plus a quadratic. And the quadratic basically says, please try to make xi close to x bar k minus uik. X bar k is the average in the last round, and so that would be sort of the consensus opinion. By the way, because these functions are convex, when you average, things get better. In fact, that's the definition of convex, right? So that's what this, that's the idea. And so it's actually very, I mean, you could think of this part as a regularization. It says, please minimize your private function, but please, try to be close to the last general opinion. That's regularization. And then this thing is interesting. This UI, it says, please be near minus UI. And then we'll look at what UI is. UI is this. This is the opinion of the ith agent. That's the average opinion. And so this is actually the deviation or error. If these were all 0, it would mean everyone would be in consensus and you'd be done. So this is the error. And this equation says u is the running sum of the error. So this is integral control, is what this is, right? OK. Anyway, that's the algorithm. I mean, you can have fancier versions of it and blah, blah, blah. But basically, I mean, that's it. Oh, I should tell you the theory behind this. So here, I'll tell you the theoretical result for this. It's this. It always works. Like always. If Fi are convex, it works always, period. There's no exceptions. OK? So that's the theory. Right? I mean, it doesn't usually work like that. Usually there's something about, oh, this is differentiable and this Lipschitz guy. And of course, you don't know any of those things anyway. But OK. But in this case, it's really simple. Right? OK, so that's it. So this just crying out to be implemented as in a distributed way. And so the way you do it is you'll have these things reside locally on agent I. And then what you'll do is you'll update all the xi's and the ui's locally. Each xi, they'll support one method, which will be basically, well, the master could drive it. The master does nothing but collect the x's, average them, and then broadcast them. So now, actually, if you know about distributed stuff, that's actually done. That's called an all reduce. But just to make it clearer and more amateurish, I'll show you an amateur implementation, which fits it's immediate. Right? So, OK, so here it is. And the point of this is that you can do this just so easily once you have an actual language. OK, but that's fine. So it goes like this. So you have a bunch of workers, right? And they're going to do this. They're going to have a parameter. A parameter is something that's changed, and you don't have to reparse the optimization problem. And if you read through it, it's just beautiful, right? This takes whatever your function was. It adds to it that augmenting term. I mean, it's just extremely close to the mathematics, right? And then this is called the proximal operator, by the way, when you minimize that. So this is an object, and it's a minimization object. If you call the solve method on prox, you're essentially evaluating the prox method, the prox function, right? And then it's as dumb as this. So what you do is you send down the pipe. The pipe is going to go to the master. You send down the pipe, your value, and then you wait. You wait to get the average, right? So this is it. And it'll hang and just wait for a bit, and then you'll get it back. And then when you do it, you update the dual variable, and then it repeats. So that's it. So this is 2 slides. This is what the master does. It's incredibly dumb, right? All it does is it listens on all the pipes. When all of these have been received, it adds them and divides by n. By the way, this is a terrible implementation, but still, the idea is it does work. It does work. And then you scatter them back, right? So actually, the point of this is not, I guess the real point of this is, the algorithm's known and all that, is you can do real things in a total of 12 lines of code. I mean, actually, this will actually run on this thing will run. You can run this on, 150 cores or whatever, something like that, and it'll actually work. OK, so we'll do a quick example. So we're going to make a support vector machine classifier. So you have a whole bunch of vectors here and a bunch of Boolean outcomes. And we're going to make an affine. We're going to choose W and V. Those are the parameters. That's the variables. And we're going to do that. Support vector machine says you do that by minimizing this piecewise linear loss function plus that regularizer. And we'll split the data up and then make a distributed SVM, right? Consensus SVM, right? And so we'll do this. By the way, this is actually kind of a tiny problem. You can solve this in about 5-10 seconds using a GPU, because that amount of data will actually fit in a GPU. But that's not the point. The point is that something actually happens, right? Oh, and I mean here, if you did it serially using an interior point method, which would be a pretty poor method, a single thread interior point method, it would take hours. Again, don't take any of this too seriously. It's just that it actually did something. And you can do the same thing in like 5 minutes for this problem. For this particular one, by the way, you'd be way better off, calling custom codes for that, like libsvm or something like that. That'd be way better. Or you can do something on a GPU or whatever. But the point is, it actually just kind of works. And this is actually what happens. And I mentioned this just because it's fun to say something about it. So one of these shows, I guess the blue, shows you your error. It's how much all the opinions are diverging. That's going to go to 0. It's going to take 500 iterations. Okay? So roughly, right? And it's going to very slow, 1 over k convergence, right? This is what you really care about. All you really care about is getting a good classifier. And you check that by testing it on a test set, right? And then this is the quality of the classifier. And it turns out on the 10th iteration, you get a classifier as good as you're ever going to get. Right. So anyway, I like showing that to people who do optimization because it pisses them off and stuff. And they say things like, oh, this has 1 over k convergence rate and stuff like that. And I was like, well, I can tell you several reasons why we don't have to worry about that. But well, one is that since it's all over at 10 iterations, it doesn't really matter that much. So, OK, so that is it. That was my ultra compressed talk. And I even probably have time for like a couple of questions and stuff. Yeah. Thank you. Yeah.
I was wondering if you had a sense for how small the set of constructive convex functions that you can get through this synthesis method is compared to the set of all convex functions.
Well, there's a lot of convex functions, like an infinite number. So probably, I understand your question, and I would put it another way. I'd put it this way. Like, if we could look at convex problems that people solve. And we'd look at lots of different fields. We'd look at finance, control, signal processing, image processing, vision, networking, circuit design, information theory. We'd look at a bunch of fields, and then look at the kind of problems they solve. That can be covered with a pretty small library. Typically, an implementation might have 20 atoms, and those are not, that's not the minimum set either. You probably get that down to like, I don't know, 5 or 10, and then go from there. So pretty small. But it's a good question. Yeah?
Is that classification error visible? Like, do you know when you're looking at it running that's
yes.
Exactly what that error is?
Yes. You know exactly. Yes. At the 10th iteration, you know what this is. However, I was a little bit, what you don't know is that it's not going to get better. Yeah. So that's what you don't know. So to be fully honest about it, but yeah. But sure, you know it because you spit out. It spits out you get something.
Yeah, and you can compare it to your variance, which is.
Yeah, you don't even need to. I mean, right? Because all you're doing is you take the consensus model at each step, and you just apply it on some data it's never seen and see how good a classifier you have. So it's nothing fancy.
So
yeah.
You said convex, deep learning is all
right.
range, and these are deeply non-convex functions.
No, they're convex. I'm just totally joking. Yeah. Okay. Yeah. Yeah. They're not. Yeah.
So what's your take? I mean, why is it such a?
I mean, I think it's fine. I think I think it's fine. It's great. I mean, I'm all for it. I mean, people act like it's like one or the other, but the real truth is, if you know these things, then you're exceedingly effective at a lot of problems.
Really
Yeah.
That you work for days and days and days.
Right, yeah, but you do that offline, right? So I think of them as that they're coming up with unbelievably good, I mean, in the machine learning case, they're coming up with unbelievably good data-based features to which we can apply these things. So I think it's fine. I mean, especially if that's done offline and this is done semi-online, then I think it's just fine. So I think they play nicely together as far as I can tell. So there's certainly, yeah. Yeah.
Since you're perfecting the desecration of mathematics in your talk, I have a question about education.
Yeah.
When we teach this stuff to kids, how should we teach it? Should we just give them the recipes? Or what's the level of depth they need?
Well, interesting. I mean, this was a 20-minute talk, right? So it turns out, I mean, in 20 minutes, you can get some of the gist of it. One nice thing about arranging stuff like this, right, is that it's actionable right off the bat, right? So you could take, I mean, there are some very interesting things in teaching, let's go high school, right? I think you can teach high school people this. It's not some, right? And you would, but the key, actually the first thing that's very interesting is you have to explain to them this whole idea of using optimization, that you have to shift from saying what to do to a different idea where you're actually saying what you want to be done and then delegating, right? Because that's what this is, right? This was, I don't know what the stupid classifier is. It's 1,000 coefficients. It's probably sparse. I don't know what it is. I don't even care, right? But the key was not that I should look at the error and say, oh, look, you know, this thing was happening, so I'm going to increase that coefficient a little bit. I mean, that's like PID design if you're talking about control, right? This is more a more modern thing, where instead what you do is what your interface, a user's interface to it is saying what you want, which is specifying an objective and constraints. So I think, and then people say, how do you do that? I mean, I'd say it in my class, I'd just say, none of your business, at least for the next 4 weeks. And then after 4 weeks, after we've done a lot, then I'll tell you how it's done. And it seems to be okay. It makes some people nervous. Is it officially lunchtime now?
It's officially lunchtime.
Good. Okay. Happy birthday, Shankar. So.